Hello, and welcome to our presentation on the selective laser sintering additive manufacturing process. My name is Ian Spital, and I am accompanied in this presentation by
Ian Steffes,
Payton Branch,
Ethan Vianney,
and Brian Lutton.
We'll first hear from Payton, who will review the history of SLS.
Thank you, Ian. So we're going to start this off with the history of additive manufacturing as a whole, and then the history of SLS in particular. So additive manufacturing is a shaping process that is similar to material removal or solidification. It's involving the addition or fusion of raw materials, is often built up in thin layers, and is used to form the final part geometry. There are 5 different types of additive manufacturing. The first type of additive manufacturing is material extrusion, which includes FDM or fused deposition modeling, FFF or fused filament fabrication, and CFF, which is composite filament fabrication. The second type of additive manufacturing is light polymerization. This includes SLA or stereolithography, CLIP or continuous liquid interface production. The third type of additive manufacturing is powder bed fusion. This includes SLS or selective laser sintering. That is what our presentation is going to be about today. SLM, which is selective laser melting, and EBM, which is electron beam melting. The fourth type of additive manufacturing is material or binder jetting. And then the fifth type of additive manufacturing is powder fed, or this includes DED or directed energy deposition. And now for the history of SLS in particular. It was first patented in 1986. It was developed at UT Austin by Dr. Carl Deckard and Dr. Joe Beeman. The early SLS machines that they made were originally produced under the name of Desktop Manufacturing Corp, or DTM. They were patented for the use with powdered metals, polymers, and ceramics, and was mainly for low-volume prototyping, one-off replacement, or space-sensitive facilities. They were comparatively low cost relative to casting or other powder metallurgies. They were less wasteful than machining and does not require specific tooling and allows for complex part geometries not feasible with other manufacturing methods. The image here in the center is a U.S. patent drawing from Deckard's SLS process in 1989. Thank you, and next up is going to be Ethan.
and that leads us on to our next slide, which is about the SLS process and industry. Some of the modern applications of SLS are that they can be used in one-off functional prototyping. They can be used as sample models and can be used in small batches of end-use components, as well as sometimes SLS can be used for higher complexity geometry. Most of the SLS materials that are used come from a variation of nylons, such as nylon 11 and nylon 12, and they can also have carbon fiber infused in them. They can also be used with a couple other polymers like TPU. The SLS process is able to be used in a wide variety of applications like aerospace, electronics, and even in some medical or military uses. And the SLS manufacturing process has 3 components to it. There's the setup, the manufacturing of SLS, and the post-processing. In the setup, the machine needs to be maintained, and this includes cleaning of the laser window, cleaning of the filters, the excess powder has to be taken care of, etc. and the powder must be prepared before every time that you want to run the SLS process. The manufacturing is broken down into 5 main steps. You have step 1, which is preheating. Step 2, the powder being dispersed using rollers. Step 3 is laser scans across the surface and sintering the part layer. Step 4 is that the bed moves down, and then step 5 is to repeat to build 3D geometry. And then the last step to the SLS process is the post-processing, which is part cooling. So you need the part to cool, set out, and you also need to clean the parts and recycle the powder.
Now that we understand the manufacturing process of SLS and the steps required to actually manufacture a part, we can take a closer look into the use case of SLS machines for specific manufacturing roles. SLS machines are used by many manufacturers, but they have a significant use case with automotive manufacturers. In general, SLS can be used to produce proof of concept models. These models are used to ensure fitment and validate the rest of a product, which couldn't be done in 3D software. Since SLS is a very fast way to produce complex parts, if there are any fitment issues, manufacturers can redesign the part and reprint it to retest and ensure fitment of that product in the larger system. SLS is also used in wind tunnel testing, where several scale models of a car or bumper product could be made and evaluated to see which design is best, and then later modified to incorporate all of the best designs and then reprint, retest to ensure success. Since SLS has very rapid manufacturing capabilities, it is an excellent tool for industries aside from automotive manufacturing, where issues will arise very quickly and need to be solved very quickly. There are uses in the medical field and governmental military sectors where parts or equipment need to very quickly be produced to potentially save a life or fix whatever issue may be at hand. SLS also gives you the ability to manufacture very complex parts, so it's excellent for creating investment casting molds or jigs to use while welding larger parts together. As tooling may need minor modifications, another design of SLS allows you to very quickly and easily modify and remanufacture those parts, so you're not having to change an entire mold for, say, a injection molded part. You could just very quickly redesign it in 3D space and reprint it to meet whatever needs that you need. Lastly, SLS is catered to the end user of a product. It is not intended to produce large-scale products for a company to then sell to the end user. The company manufacturing the product using SLS is meant to be the end user. This is because SLS is very customizable and it's very complex to use, but it is not suitable for large-scale manufacturing. There are better ways to make similar products than SLS. It's generally meant to be used as one-off products for making tooling or jigs, where it would otherwise just be so expensive to do it using injection molding or other manufacturing techniques. So SLS is meant to be used internally at the company for all sorts of different reasons, primarily making tooling.
Seen here is a quick video of the SLS process, specifically sintering and dosing powder. Now that we've demonstrated some of the broad use cases for SLS in modern industries, I'll be presenting a more targeted case study on SLS additive manufacturing, using Boston-based Formlabs as an example on the supplier side, and my co-op company, Commute, as a consumer and manufacturer. To begin, Formlabs is a 3D printer manufacturer headquartered in Boston, Massachusetts that specializes in low-cost, commercial-grade SLA and SLS devices, and who market themselves as one of the largest suppliers of such devices in the world. Their SLS lineup, known as the Fuse series, is currently limited to the Fuse 1 and Fuse 1 Plus 30 watt, pictured on the top right. Both models, which are made distinct by the power of their sintering laser, are marketed as benchtop devices comparable in size to a 50-gallon trash bin, which makes them much smaller and easier to install than room-height SLS devices like the EOS Formiga, pictured on the bottom right. In concert with this reduced size, the fuse is priced at around $19,000 or $22,000 for the Fuse 1 plus 30 watt, which, while still substantially more than a consumer-grade FDM printer, is comparatively low against the $100,000 plus price of larger industrial SLS devices. Alongside these printers, other parts of the Fuse lineup are the Fuse Sift and Fuse Blast, which, together with their SLS printer, comprise a comprehensive setup, manufacturing, and post-processing workflow. The Sift is used to prepare the mixed nylon powder for the printer, which typically uses a 30 to 40% refresh rate, signifying a ratio of 60 to 70% old powder from previous prints and 30 to 40% fresh powder. This station also includes a vibrating sifter used to break up packed powder after a print is complete, which then feeds into the refresh hopper for the aforementioned powder mixing. Other entry in the Fuse lineup, the Fuse Blast, is a newer offering that automates the sandblasting step of post-processing in SLS. This not only cuts down on the manual labor involved in the SLS process, but also helps ensure a more uniform surface finish compared to parts blasted by hand. Moving to the consumer and manufacturing side of these Formlabs products, I have used the Fuse 1 and Fuse Sift extensively in my time at my co-op company Commute, a startup based here in Flint that manufactures micromobility charging infrastructure. We use the Fuse SLS printer to create both functional prototypes and final products, especially for the adapters that allow micromobility devices like e-scooters, pictured in the bottom left of the slide, to park and charge at our hubs. In my experience, the SLS printing process itself is relatively simple to execute, as the software and printer handle most of the settings and part packing automatically. However, the setup and especially the post-processing steps can be quite labor-intensive. Without having an automated solution like the Blast, I've spent numerous hours manually brushing powder away from batches of parts and then sandblasting them. While experience has made me more efficient over time, I still can't achieve completely uniform results, especially in sandblasting, where we risk leaving a surface slightly marred and darkened if the air gun is too close to the part or held in one spot for too long. Another note about our use of SLS is that we usually do not use it for initial stages of prototyping, as even with the high refresh rate, this would use up expensive nylon powder. Instead, we rely on comparatively cheap rough prototyping and PLA on consumer-grade FDM printers, then step up to sintered nylon for higher dimensional tolerances when we think a design is approaching a finalized or production-ready state. Next, you'll hear from Ian Steffes, who will elaborate on the advantages and disadvantages of SLS I alluded to during this slide.
Thanks, Ian. I'll be going over the advantages, disadvantages, and considerations for SLS on this slide. Some of the main geometry considerations are overhangs and geometry constraints are less restrictive in SLS due to how the powder works. You can because of the powder, you can also have hollow structures for more efficient prints. It encourages the use of hollow shell-style structures to reduce the material usage. This reduced material usage adds into the powder recycling, which is the fact that because there's powder that gets used when you make stuff, it also is powder that doesn't get used, and you can reuse that powder in future prints. There's also some disadvantages to SLS. So one of the big disadvantages is post-processing challenges, which is because it's a very labor-intensive process with limited automation. You really don't want to do any low-quantity prototyping because it's very ineffective for that. And there's also health and safety concerns. Because of the fine powder, it possesses a health hazard. You need a bunch of PPE like masks and respirators, as well as for the masks you need carbon filters and a bunch of stuff like that. You also need to worry about the fumes as melting nylon produces them, which can pose a potential risk. Ian Spital has told us that when he works with them, he's noticed that there's also a smell from it, which is unknown if it's a bad risk or not, but it's still something to worry about. Print failures and warping are also a big disadvantage because they're unrecoverable failures that need to be that require you to restart another print if they happen. The risk of warping is due to residue and powder buildup and slow cooling requirements after printing. There's also some considerations to make when using this process, like wall thickness importance. It's a critical consideration to prevent the part from breaking during brushing or sandblasting. You also need to consider post-processing and powder. You need to incorporate features through holes and pockets to facilitate easy removal of excess powder, minimizing waste. If you don't do this, it could cause other various advantages or disadvantages. You also need to consider product life. Because nylon is durable. Thank you, and we will move on to the summary now. To summarize, SLS is a form of additive manufacturing under the bucket of powder bed fusion. Used for one-off functional prototyping, sample models, small batches, and end-use components. It is designed for entry-level commercial use. There are many pros to SLS, such as geometry considerations, hollow structures for efficiency, and powder recycling. There are also many cons to SLS, such as post-processing challenges, health and safety concerns, and print failures and warping issues that are unrecoverable. There are also some considerations to keep in mind for SLS, such as wall thickness importance and the product life. I will now pass it off to Ian Spital to do the sources.
Here are our sources for this presentation. Thank you for your time. If you have any additional questions about the SLS process or our presentation, please reach out to me at spit7999@kettering.edu.